Hello everyone. In this video, we're going to learn how to convert an Ethereum smart contract to a Solana smart contract. And this is for you, a Solidity dev, and you want to know how things works in Solana. In this lecture, we'll be converting an Ethereum smart contract written in Solidity to a Solana smart contract written with Rust. And before we dive into that, let's try to understand how the smart contract works in both Solana and Ethereum. The major language used in writing Ethereum smart contract is Solidity, while the major language used in writing Solana programs, or you can call them smart contract, is Rust. How smart contract works. A smart contract is a computer program stored on a blockchain. Smart contracts are self-executing pieces of code that execute when the preset conditions by the involved parties are met. For example, a smart contract that issues a token when someone deposits fiat. The way smart contract works in Ethereum is not the way it works in Solana. Each languages, each platform, each blockchain has their own model and set of rules in order to write their smart contract. In the next slide, we'll be examining the unique differences between the Ethereum and the Solana smart contract. Unique difference between the Ethereum and the Solana smart contract. Apart from the language used, the major difference between Ethereum and Solana smart contract is state. State in Ethereum refers to the information that a node must hold in order to be able to process new incoming blocks and transactions. In Ethereum, states include the account balances and losses, the contract code, the contract storage, and consensus related data. Smart contract written in Ethereum can store state, but smart contract written in Solana cannot store state. Instead, account is being used to store state in Solana. A good example of how state works in Ethereum is the ATM. The ATM can be seen as the program or the smart contract, while the cash in the ATM can be seen as the state. The ATM stores the cash, and when users interact with the ATM, it changes the state or the amount of cash present. It also stores and updates the necessary informations like the amount of cash present, the amount of cash withdrawn, the number of transactions processed, the picture of the user, etc. Still on the unique difference between the Ethereum smart contract and the Solana program, there is this concept called account in Solana, and account is defined as a record in the Solana ledger that either holds data or an executable program. The executable program can also be called the smart contract itself. So an account could either be a program account or a data account. Solana program or smart contracts do not store state. The account model is used instead. So the program itself, the smart contract itself, is being stored in a different account, and the data that the smart contract is going to be modifying, it will also be stored in a separate account, which is how the Solana smart contract works. A good example of how accounts work in Solana is the vinyl music player. In this case, the music player itself represents the program, while the vinyl disc being played represents the account. The music player, which is the program, only interprets the data being stored in the vinyl disc and produces an output sound. It does not store the data, only the vinyl disc stores data. What does an account stores? An account can store LAN ports. It can also store the owner of the account itself. It can also store executable program. It can store data, and it can store rent. Now let's proceed and see how we can convert a Solidity program to a Solana program. This is a simple Solidity smart contract named counter. It does a simple task. It has a variable called number, and it has a constructor. It has a method increase, which increases number by 1. It has another method called decrease, which decreases number by 1, and it has a method called getNumber, which display the current numbers. So if I try to deploy this contract now, and let's start with 8, and I click on the deploy. So let's try and interact with it. Let's start with the get number. So get number, we have 8. So if we increase it and we click on the get number, we have 9. If we decrease it and we click on the get number, then we have 8. So we'll be converting this simple smart contract into Solana smart contract, just for you to see how things works in Solana. This is an online ID used for writing Solana programs, just like we have Remix in Ethereum. And when writing Solana programs, you can either use the vanilla Rust or you can write it using the Anchor framework. I personally prefer using the Anchor framework because it is a lot easier when using the Anchor framework. So this is a simple smart contract, and we can divide this simple smart contract into 3 sections. The first part is the program section, which contains the logic of the smart contract itself. The second section is the account section, which handles the serialization and serialization of accounts. And the last section is the state, which stores the state, or we can refer to it as the custom data we would like our, or we will want our smart contract to store. The first line here, where you can see they use anchor lang, the prelude star, is just a way of importing the modules we need to use in order to write the smart contract. The next line is the declare ID, and there's an address. This is the program address. Like we said, we have 2 types of accounts in Solana. We have the program account and we have the data account, and this is going to be the program account. And what this line is just trying to do is going to ensure that the program owns the account is trying to edit, like the program account owns the data account it's trying to edit. So the next line is the program section, and the first thing we can see is the MODLO. The MOD stands for module, and the next line is LO. This line stands for the name of the smart contract itself. And so when converting an Ethereum smart contract to a Solana smart contract, the first thing to do is to look out for the state variable. So what are state variables in Solidity? State variables are variables whose value are stored permanently in the contract storage. As I said earlier, Solana smart contracts do not store state. Account is used instead. So we have to create an account for all the state variables. So how do we create an account in Solana? An account is created like this. Let me delete this so it can be clearer. You create a struct. So how do we create a struct in Rust? You write it like this, struct. Then the name of the struct you are creating, let's call it new account. Then you open a curly braces. Then the data we want to store in this struct, we list them. In our case, we are storing a number, so let's write number. Then the data type, let's store it as an unsigned 64-bit number. So yes, we are good to go. Then we need to make our struct public so that the program can have access to it. And we also need to add a trait called account. So just like we said, we have 2 types of account. We have the program account and we have the data account. Program account can't just modify any data account. It has to have authority to modify the data account. So for it to have the authority to modify the data account, we have to put this account to it so it can be able to have authority over this account. After creating the account, we need to be able to pass the account to the program. Remember when I gave the example of the vinyl disc and the music player? The vinyl disc serves as the account while the music player serves as the program. We need to place the vinyl disc on the music player so the music player can be able to read the content or the data in the vinyl disc and play its content as a music. In Solana, the way we pass account to the program or smart contract is through instructions. So what's an instruction? Instruction comprises of all the accounts, the programs or the smart contract we create, we read and modify. After creating the instructions, it must be passed as one of the program arguments. When constructing an instruction, a list of all accounts that may be read or written during execution of that instruction must be supplied. Any account whose data may be mutated by the program during execution must be specified as writable. Also, any account whose Lamport balance may be mutated by the program during execution must be specified as writable. When also creating an instructions, we have to use the struct format. So I'll delete this so you can see how an instructions is being created. So we pass in the curly braces. Then the first thing is the account. Then so in this one we're creating a new account. Then we specify the payer. Let's leave it blank for now. Then we specify the space. Let's leave it blank for now. Then we call it, let's call it new account and use the account like that, and the info and the name of the account itself. Then the next one is the signer account, and we need to pass it as a mutable, and the name itself, let's call it user, and let's give it the signer. And the last one will be the system program. Let's pass system. Yes, I've just created an instructions for this account, so I will explain how it works. Instruction is how we pass our data accounts to the program account, and when we call this initialize function, the program is going to create a new account. And if we want the program to create a new account, we need to use this trait and specify the init keyword. Now, when creating a new account, it is not free. Someone has to pay for it. So we need to specify a user. So after specifying the user, we also need to specify the space. The space is how large the account is going to consume. The next thing is the user, which is the signer. The user is the individual that will be interacting with this smart contract, and at the same time is also going to be the signer. So he's the one that will have access to it. And lastly, we have the system program. This is a program account, and what it does is it's going to be the one responsible for the creation of new accounts, and also be the one responsible for the transferring of lamp ports from the user account to the blockchain account. So we've just built the instructions for our program. After creating the instructions, we can now pass it to the program or the smart contract itself as a context. And I said earlier that it's always the first argument for the smart contract or the program. Then also when the user is interacting with this program, he wants to store a data, which is why he created the account. So he is also going to include that in the argument. So I forgot to add, when creating our instructions, we are to put a trait called derive. The derive trait will handle the deserialization and serialization of accounts. Now we've included it. So now we've created the account, we've created the instructions, and we've now passed the instruction as a context. Now we can now handle the program logic, or what we want the smart contract to do. In our case, we want the smart contract to store the data that the user is going to pass in to the argument. So let's create a variable called data account. So let's use the keyword let's call it data account. You can call it anything. Then, just like I said earlier, since we already passed these instructions as a context into this function, we can have access to all the accounts here. And for you to have access to all the accounts here, you need to use the keyword context.account. Then after using the keyword context.account, you can point to any of the accounts you want. In our case, we want to point to the new account we are creating, that is going to store the data the user is going to be passing through it via the argument. So let's call the new account, which is the name. So now that we've stored that, we can now go into this new account and modify the data inside the new account. So how are we going to do that? Let's just call the data account we created, then dot the number, then let's assign it to the data we will be passing into it, like to an argument. For instance, it can be 5, so it's going to store the 5. So let's call it data. So that's all about the initialize function. So next we'll be working with the increase function. So that will be pop increase, then it's going to return a result, which should be a result of the variant. Okay, and okay, then also we'll be working on the decrease function. So let's copy this and paste it here. It seems I forgot to add the FN keyword, so I'll just add it and add it here. So the first argument will be the context and the instructions. So let's fill it in context, and the same thing here, the context and the context. Yeah, we can use the instructions we use for initialize, and the reason is that when we click on the initialize, it's going to create a new account. But when we want to use the increase function, we don't want it to create a new account. We want it to modify the already existing account. So we have to create a new instructions for the increase and decrease. So let's start by creating the instruction. So the first thing is the derive keyword and the account, which is going to handle the serialization and the deserialization of the account, and it must be in the struct format, which must be public. Then the name, let's call it increase, and let's put a lifetime specifier inside, which will be info. Then the curly braces. Then the first thing is the account we want to mutate, which must be a mutable account. So let's call it mutable account. Then the name of the account we want to mutate, let's say new account. This could be anything, but I just call it a new account. Then let's say account, then the info, then the name of the account we want to modify, which in our case is the new account. So that's all. So let's create the instructions for decrease also. Let's just copy this and let's paste it here. So let's change this to decrease. So we've created the instruction. Then we can now pass it as a context. So we have the increase, and we have the decrease. So we can start filling the function or the logic of the function. So the first thing is, let's get this account. So let's say this could be anything, so I'll just call it data account. Should be equals to, it should be a reference and mutable to the context dot account dot the new account. So now that we have access to this new account, we can now modify the data inside. So let's say data account should be equals to, data account dot the number, which is what we want to edit, should increase by a value of 1 plus, should increase by a value of 1. So we are done with the increase logic. So let's do the same thing for the decrease logic. Let's copy this and let's paste it here, but in this time we are decreasing the value of this data by 1. So let's turn this to minus. So that's it about the decrease logic. Oh, this should be an angle bracket, not this type. So let me change it now. Then same thing here. So yeah, that's it. We also have to make this data here a mutable reference. So let's do that too. Yeah. So now that we're done with the smart contracts, we can now compile it. But before we compile, let's just change the name of our smart contract. Though it's not compulsory, but let's just change it. Let's call it counter. So we can now compile. If we are to compile, we click on the build. So and let's check the terminal. Let me make it bigger. So it's the build is successful. So after we've successfully compiled the smart contract, we can then deploy. And depending on where you want to deploy, I'm currently using the local host, but in Solana you can deploy to the local host for testing it locally. You can deploy to the devnet, you can deploy to the testnet, and you can deploy to the mainnet. The mainnet is when your smart contract will be live, but the devnet, the local host, they are meant for testing. So, and before you also deploy to the local host, I mean the mainnet, you have to test and to see that the smart contract is behaving the way you wanted it to do. So in our next lecture, we'll be using VS Code, and that will require us to install some libraries, some applications. For example, you have to install Rust, and you will install the Anchor. I would try and make a video on how you can do that. So let's try and compare the Solidity and the Solana Rust smart contract. So the first thing about the Solidity is the state variable number. But in Solana, we don't store state. The program doesn't store state. So instead, we have to create an account that's going to do that for us instead. And this is the account right here. This is the account right here. So the next thing is the constructor. We really don't have a constructor function in Rust, but the logic of this constructor is when you are trying to deploy this program, it should set a default number. So, and we already handled that with the initialize function. We load the account that stores the data, then passing it to the arguments, we can then store the default data. Then the next thing is the increase function in the Solidity smart contract. It have access to this state, but when it comes to the Solana, we first have to load the account that stores the data, then we access the data, then we increase it by 1. The same thing goes for the decrease, and so that's just the difference. So which one do you think it's easier between the two? Let me know in the comment section.